All right. So last time we left off, we had started talking about kinetics, and kinetics is how fast something happens, right? It's not whether it's spontaneous or not, okay? So for example, cooking things is usually not spontaneous, right? But we can drive those reactions to finish and get a finished product, which is the cooked food, right? Okay, how fast does that happen? What's it usually depend on for how fast it happens? Heat. Can anybody tell me any other ways that you can make it go faster? Anybody ever used a pressure cooker? No? Really? What? How about an air fryer? Okay. How do you guys not use pressure cookers? Oh, because we're in Tennessee, I guess. You guys don't do like slow cook stuff a lot. Yeah, I guess that's my Texan coming out. Okay. So anyways, we'll skip the pressure cooker. Pressure being one of the things you can make cooking happen faster, right? So if we look at an air fryer, what's the secret sauce to an air fryer? Has two parts to the top of it, right? Has a heating coil and a fan, doesn't it? Everybody hears the fan when it's running? Whoosh. Okay. Now that fan helps to circulate things. And so what we're doing is we're mixing the air to give it more even exposure to the heat and more exposure all over to the heat. Okay? And so mixing things is usually one of the ways you can make reactions go faster, giving more exposure. It's another way to add kinetic energy. Okay? Okay. Anybody else know any other ways you can...
Chop it up, make it smaller.
Exactly. More surface area, right? Increase the surface area of it. Make it so you can get more heat per morsel, right? Faster reactions, okay? And so we're increasing the kinetics, the rate of the reaction in these, okay? It didn't change if it was spontaneous, did it? If I chop something up, I throw it in my fridge, is that thing cooking? No, it's never cooking, right? So I didn't change whether it was spontaneous or not, did I? All right, so can anybody else tell me any other ones? Huh? Catalyst, yes. Can you tell me what a food catalyst would be?
Baking powder, cakes, or stuff.
So those ones aren't a catalyst for making it cook faster. Though what they are is baking powder, when you use it, actually goes to gas, CO2. And so it makes things very fluffy because you're putting air pockets in it. Okay, so we're in Tennessee, right? What's in all the food in Tennessee? Vinegar. Vinegar is an acid. And so acid is a very common catalyst that can speed up reactions. And it can cause speeding up of reactions like degradation of meat to make it softer. It can cause things like cooking or otherwise pickling vegetables, right? Very common use all over the world, right? And just about every culture, too, which is quite interesting. They use citrus or vinegar, one of the two. Very common. Okay. So right here, again, we're talking about rates of reactions. Again, this is how fast something happens. I want you to have a very clear delineation in your head, right? We have the speed something's going to happen, and then we have whether it will spontaneously happen on its own, right? So, for example, the Grand Canyon, would have that spontaneously made itself? It did, didn't it? Okay? Water will spontaneously carve through a rock, won't it? Okay? If you were to visit the Grand Canyon and observe it for a day or two, would you go, yeah, that reaction's happening? No. It's too slow, right? And so oftentimes when we get no reaction, there's two different ways that can happen. There is it's not spontaneous, so it's never going to happen. Or it's just too dang slow and it's not going to happen in our lifetime. Okay? There's many reactions happening around you right now. They're just too slow. They will never happen within the lifetime of probably all of humanity. Okay? The Grand Canyon outdates all of humanity by a factor of few million. Yeah, it took a long time to make. Okay? So you were never going to see that reaction happening. So whenever we have a chemical reaction, this is the theory behind this, okay? We would have the collision of two molecules. So we'd have one molecule here, a molecule here, okay? Let's say we're burning something, so the oxygen comes in. It would collide with the fuel, and then you would get a reaction if that collision is powerful enough, so you have enough momentum behind it, and oriented in the correct direction. For example, think of a reaction like me holding hands between my two hands, right? So if they come at each other like this, with the correct speed and orientation, I'm going to get a reaction, right? What would happen, though, if I come in like this? I don't get the same thing, do I? No. And if I came in like this, I don't get any reaction at all, do I? Okay? And so you have several factors that are going to be playing into this. And this is oftentimes actually what catalysts, especially like enzymes, do. Enzymes basically hold something in the correct orientation, so you get reactions almost every collision. And so they speed the reaction up tremendously, right? Again, though, reactions and reaction rates have nothing to do with spontaneity, do they? Just speed, okay? So, for example, if I'm holding this remote, I'm speeding up the reaction of slotting into my other hand, aren't I? But I'm also speeding up the reaction of pulling it away, aren't I? So what you're going to see is that things that speed up reactions tend to do so in both directions, okay? They're going to make it faster to go in either direction, right? Kind of like if you put rollers on something, it rolls up and down the hill faster either way, right? No rollers on it, rolls up and down the hill real slow, right? Okay. All right, so this right here, again, is going to be examples of various different reactions where we would have various different processes involved in them. And so what we can see here is, for example, this would be adding heat to it. It's going to make everything move faster, and so we're going to get more collisions, right? Okay. If we have it more mixed or more concentrated, we're going to get more collisions, aren't we? Okay. If we have less concentration, we're going to get less collisions, right? Okay. All right, so one of the major things, and the one you most intuitively probably grasp, is temperature. Keep in mind that whenever you're learning anything in chemistry, I know I'm going to give you very strict definitions and very strict terminology. Part of this class is I'm teaching you a language. That language is good for every scientific career. And do you know what careers involve science now? Is there a career that does not involve science now? No, not really. The entire world is built off of science now, isn't it? Yeah. You really can't go anywhere anymore without having science affect you in some way. Okay? And so this language is actually the language that we exist on top of. Okay? All right. So again, temperature, I remember that these are things you intuitively know. You already exist in this. You already are experiencing this. You've been cooking or seeing food cooked. You've had all this done. That was all chemistry. You living is chemistry. Okay? Everything around you is chemistry. So take a step back from it being chemistry and go, what do I know about this in my life? Okay? Okay, so again, energy in the system, which is the kinetic energy, the motion of your reacting molecules. This is how fast things are going to react. You go faster, your collisions are going to result in more energy when you impact, right? Like if you drive 10 miles per hour, the collision's not very dangerous. If you drive 100 miles per hour, the collisions are dangerous, right? Okay. So the more energy you have in a system, the easier it is for these collisions to cause something, and the more collisions you get. Okay? All right, so what is kinetic energy, and how is that related to temperature, by the way? Okay, does anybody know the two parts of kinetic energy? Okay. Okay, so kinetic energy is mass and speed. Okay, or velocity is actually the correct term, but velocity is just speed with direction. Okay? Okay, so we have these two components. That's related to temperature by the fact that temperature is randomized kinetic energy. So when you have a bunch of particles all bouncing around in different directions, you don't have clear kinetic energy going one way. Okay? And so what you can do is you call that temperature. The higher the temperature, the higher the average kinetic energy in that system. Okay? Okay. And so that's why, for example, traffic actually has heat maps. What are they doing there? Randomized kinetic energy, the vehicles, is being mapped out as if it's temperature, isn't it? Yeah, kind of interesting, right? Okay, so as a result, they're going to collide more reactions are going to occur, and these collisions will be more meaningful because on average they'll have more energy in them. Okay? The amount of the reactant is going to change how fast a reaction goes. If you put more gunpowder into a charge, what's going to happen to that charge? Bigger boom, right? Okay. Anybody ever done fireworks where they start messing around with fireworks a little bit? Or do you have really responsible parents? Okay, I guess everybody had really responsible parents. That's a little sad, actually. Probably good for you having hands, but okay. But everybody's familiar with this idea of more explosive powder, more explosive stuff in it, bigger boom. Okay. And again, that's more reactant, right? The more reactant you have, the larger the result. Okay? The faster the reaction can go. And explosions are just very, very fast reactions. Okay? All right, so again, remember that as you react, what's going to end up happening is you're going to use up your reactants, and then you're going to slow down that reaction. Okay? What happens to a candle when you get to the very end of the fuel? It starts sputtering, and the flame shrinks a bunch, right? You're seeing a reaction that's going slower and slower as you consume the fuel. Okay? All right, so the presence of a catalyst, excellent. I was really glad people brought that up. Fantastic. And so catalysts are going to speed up a reaction. They're actually going to do this by lowering the activation energy. So think of the activation energy again as a hill. It's a hill that's between the start point and your destination. Okay? So if I have you have to walk from the dorm to your class, and you have to scale Everest to do it, are you going to get to your class very fast? No, it's going to be a very slow. Even though you going down Everest is fairly easy, right? Surviving that down is pretty hard. But going down, it's real easy. Okay. If I shrink that hill between you and your destination down to a little tiny speed bump, you going to get to class okay? Yeah, you're going to get to class pretty fast, right? In fact, you did it today, probably. Okay, there's speed bumps all around here, right? All right, so, again, this is going to reduce the activation energy. Now, let me ask you a question. We have the spontaneous of you coming to class, right? Okay. Okay, we then have a non-spontaneous reaction, which would be you going from class to your home, right? That would be the opposite reaction. Okay? Does increasing the hill make that slower as well? It does, doesn't it? It'd be slower going back as well, wouldn't it? If we reduce the hill, what does that do to your ability to go back home? Makes it faster, doesn't it? Yeah, so catalysts do it both ways. They make the reaction faster, both directions, because they lower the activation energy. All right, so remember, one of the important things about a catalyst is that it's going to participate in a chemical reaction, but it's going to ultimately remain unchanged, and it's going to end up being the same at the end as it was at the beginning. Okay? Catalysts are not consumed in the reaction. I don't know most of you have ever actually seen this. You've all used a catalytic converter, but a lot of you probably don't know anything about it. Is that a correct assumption? Okay. There's not a lot of catalysts that I can point out in your daily lives that you would actually know anything about. If you know anything about a catalytic converter, that is a catalyst. The catalyst inside of it is actually a pretty expensive metal. That's why people cut it out of your car and steal it. But it actually converts like the NOx, the nitrogen oxides, which cause smog, photochemical smog like you see in LA, back into nitrogen that's in the atmosphere already, the N2, and that prevents photochemical smog. It also converts the carbon monoxide that might otherwise escape into carbon dioxide. Okay? And so has anybody ever seen hopefully not in real life, please not in real life, but somebody trying to suffocate themselves in a garage by running a car? Seen it in the movies, hopefully not in real life. Okay. That is actually not something you can do with any modern vehicle that's under decent repair. A catalytic converter will convert it to CO2. It will take you about 8 hours of running your car continuously just to fill up enough CO2 inside the car for you to even experience lightheadedness. So what ends up happening now is people try that with a new car. Somebody comes into their garage in the 8 hours that they're sitting there, and it goes, "What are you doing?" And then they're like embarrassed and have to figure out how to answer that. So it is not an effective method to kill yourself. Okay. In fact, very likely you would never be able to actually kill yourself. You'd run out of gas before you'd actually kill yourself. You might go unconscious towards the end, but that's about it. Wake up with a really bad headache. Okay. So, not actually something you can easily do. Now, funny enough, Volkswagen actually got busted for having a program in their cars that would change the catalytic converters, how it ran, depending on if the EPA was testing it or not. So, every now and then, there's not correctly functioning catalytic converters. Okay. So enzymes, these are going to be biological catalysts. Most of the biochemical reactions will use enzymes to increase the reaction rates because reaction rate is very, very important for living organisms. If it's too slow, you would obviously die before you actually finish it, right? Okay. And so most of the enzymes are proteins. There are RNA enzymes as well. In fact, the protoenzymes were probably RNA, okay? But there are actually still quite a few enzymes that are partially or fully RNA. Okay. The enzymes can enhance the rate of chemical reactions. They can do it by a factor of more than 10 million for some of these reactions. The enzyme that you have that converts CO2 into carbamic acid and carbamic acid into CO2 back at your lungs so you can breathe it out does this millions and millions of times per second. Okay. One of the fastest enzymes in your body, and one of the fastest enzymes ever recorded. Very impressive enzyme. So what enzymes do is they increase the speed of reactions, typically by immobilizing the reactants at the site of the enzyme. This is going to be called an active site in the enzyme. This active site is going to orient them in the correct orientation so that every collision they do is very close to the correct orientation for them to react. And so it greatly reduces the activation energy. Again, though, keep in mind it does not change whether the reaction is spontaneous. Okay? And so you have to depend on other things to change the spontaneity of the reaction. Typically, that would be inclusion of something like ATP. Okay? You would include ATP in the reaction. That provides energy. That makes the reaction spontaneous. Okay, if anybody was curious, by the way, I used to teach biochemistry and have taught biochemistry for like 15 years. Used to do it at the med school at KU and stuff. So if anybody's curious about like biochemistry and stuff, come on and talk to me sometime. All right, so enzymes are going to be highly specific to the reactions that they catalyze in the body because they're going to specifically fit and bind to what are called the substrates. The substrates are the ingredients in that reaction. Okay? So when they are defective, the result's often going to be a disease state in your organism because you will no longer have that reaction, and those reactions typically are joined into what are called pathways. And so you can be missing part of a relatively small reaction that cascades to you not having entire classes of enzymes or amino acids. Okay? And so it can actually spin out pretty quickly. So albinism, is the lack of pigmentation in the skin, hair, and eyes. It's caused by a defect in tyrosinase, which is an enzyme in the pathway that produces the pigment, which is melanin. So the pigment melanin is what gives us our colorings. It's what creates things like you having a blue, green, brown, etc. eyes. Your skin color, of course. Your tanning, when you tan, that's melanin again. And it also creates the pigmentation in your hair. Okay? All right, so this is some different diseases right here, and these are the enzymes that are responsible for this. Now, keep in mind that some of these enzymes, diseases, are genetically caused. Some are genetic predispositions towards it. So you could have the genetics, for example, gout, and yet never develop gout in your entire life. Okay? Because you have the correct diet that allows you to have your somewhat defective enzyme still function good enough. Okay? This is actually true for a lot of diseases where they have genetic predispositions, but they may never actually trigger. Okay? And a lot of that has to do with actually your diet, especially before you actually start experiencing symptoms of the disease. Okay? So, by the way, get genetic testing for diseases if you have any diseases that show up in your family. And there's oftentimes things you can do to never experience the disease. Not true for every disease, but actually quite interesting. Okay, so this is gout right here. This is actually the enzyme that's defective in this. This is the clinical symptoms. Does anybody know gout? Ever heard of it before? Okay, anybody know what it used to be called? The disease of kings. Because the genetic predisposition, again, it requires a dietary to actually start triggering it. And people back 200 years ago couldn't get enough of the foods that caused this to actually ever experience it. So only people that were very wealthy could get those foods in the amounts that would actually trigger this. Yeah. And so gout's actually has become like a thing in the U.S. quite a bit because we just have so much wealth, right? So much food that we can get. Okay, anyways. This is lactose intolerance. It's lactase that's deficient. It can be quite a range of this. We have complete lactose intolerance, and you don't have almost any functional lactase, or just slight misfunctioning of the lactase. Diseases can also be built up over time, meaning that you, over time, start developing deficient enzyme, or you start developing resistance to the enzyme. Okay? All right, so let's talk about synthesis reactions. These are going to occur when smaller molecules or atoms combine to create larger molecules. Synthesis reactions often require energy because their products are going to have higher free energy, i.e. less random, than the reactants, which are more random. The more molecules you have in a system, the more randomness. If you start combining those molecules to make bigger stuff, you have less molecules, less randomness. It's going to end up being non-spontaneous mostly. Okay. The other one, the opposite of this, will be decomposition reactions. These are going to be used to break apart larger molecules into smaller molecules. Decomposition reactions often are going to give off energy because products will compound, which form stronger bonds than the reactants. These reactants are only going to have only one reactant usually. So you have a reactant, you break it apart, you decompose it into two simpler things. Okay. Exchange reactions, these are oftentimes called displacement reactions. They're going to involve both a synthesis and a decomposition. They're going to be an exchange. So you lose a group, you gain a new one. Okay? All right. So this right here is a nice little overview. Here we have amino acids being used to synthesize a polymer. Did anybody realize that's a polymer? Okay, amino acids synthesize a protein or a peptide, right? Okay, everybody knows proteins? Okay. All right, so the amino acids are actually monomers. They're combining together to make what's called a polymer. Polymer as in like plastic. Okay? So that is a type of polymer. I know. You never realized it, did you? Okay. This is a what type of reaction, by the way? We combine smaller things to make larger. That is a synthesis. Yeah, we're synthesizing protein, aren't we? Right here is starch going to glucose. You actually do start this process in your mouth whenever you eat starch. This could also be like glycogen in your body being used to produce glucose. Glucose is the only thing your brain actually uses for energy. And so this reaction is what type of reaction? Taking something large, splitting it up. Decomposition. You got it. You got it. Okay, and this one right here, this is going to be an exchange reaction. So we have here molecules, and what we're going to see is that these compounds here are going to exchange. We're going to have the chloride exchanging with the hydroxide. Everybody see that? And so what we end up getting is MgCl2. Notice we just exchanged or flipped these, right? And this right here gives us H2O. And so again, we have compounds coming in, compounds going out. We're just exchanging the groups on them, right? Okay. Again, this right here is your general reaction scheme in a sort of simple to read table. Exchanges can actually be broken down into two types of exchange. There is the single exchange, where we change one group over and we just transfer one group to another. Okay? And then there's the double exchange. That's like the one we saw before with the HCl, and that's going to be where you have both of them that exchange something. Okay? All right, so let's talk about reversible and irreversible reactions. So reversible reactions can form products in either direction. So your process is spontaneous in one direction, but then you can non-spontaneously push it into the other. The CO2 going into carbamic acid, then carbamic acid going into CO2. This is reversible. The other way to look at it is the boulder. You push the boulder up the hill, right? You let go, the boulder rolls down the hill, right? And so that reaction is also reversible. Okay. If a chemical bond can be formed with enough input of energy, it can usually be broken as well. Reversible chemical reactions are going to be indicated with a pair of arrows between the reactants and products pointing into opposite directions. And apparently, the last update of my my PowerPoint doesn't like that symbol anymore. So what it looked like, it would look something like one of these two symbols. Okay? This denotes that that is a reversible reaction. Okay? This specifically is one that's going back and forth at about equal directions, about equal amounts. Okay? Okay, so this right here is going to be a forward reaction. This occurs when A and B form AB. So when a sufficient amount of the AB builds up, the reverse reaction would then occur, and so this reaction would start flowing backwards with this breaking up. Okay? This would eventually create what's called a chemical equilibrium. This is where both reactions start occurring at the same rate. So what you end up getting is no overall change in the amount of A or AB, but you have continuous exchange between. Okay? Easiest way to usually think about this in your head would actually be with a, anybody ever been to a nightclub or theme park with a cap to the number of people that can go in? Okay, so what do you see at the door for that? 2 people come out, 2 people go in, right? 3 people come out, how many go in? 3, yeah. And so that would actually be a form of equilibrium, right? Where you have continuous exchange between, but overall states of both crowds doesn't change much, right? Okay. So this does not mean there are equal amounts of reactants and products. That is not what is equal in a chemical equilibrium. What's equal in a chemical equilibrium is the exchange. How fast these 2 reactions are going back and forth. Okay? The amounts of each reactant does not need to be the same at all. Right? In fact, the nightclub situation I was just describing, those are almost always not the same at all, right? If it's a good nightclub, then the outside is a lot more people than the inside, right? Okay. Yeah. Or Disneyland, also. Same thing. Not equal crowds at all, right? Okay. All right, so keep in mind, again, in a equilibrium, chemical equilibrium, or dynamic equilibrium, these are all terms for it, you're going to have continuous exchange between the 2 states, and they will be equal in the speed they're going back and forth. So you'll experience no overall change, but the individual molecules, the individual items, will continuously exchange between the 2. Okay. So reactions are going to be either highly exothermic or are, for practical purposes, can't really be done the other way, are going to be what's called irreversible reactions. More often than not, this is because you go to a gas and then you don't have a contained system. And so more often than not, this is irreversible reactions for things like combustions, because you form a gas, it then goes off, and you can't get it back. Okay? So that's one of the most common forms of irreversible reaction. A great example of an irreversible reaction, has anybody ever seen like a trebuchet or a cannon? Okay, you got the reaction of the explosion, right? And it throws the ball out. Can you get the ball back? Get the reaction to run in reverse? No, because the ball's gone. Goodbye, ball. Okay. When we break down food, these chemical reactions are never going to be reversed to reform the actual food. Instead, the energy is produced. It's then used to form other molecules and maintain bodily functions. You don't get the food back despite you putting energy to it, right? Won't get the same proteins, you get new ones. Combustion. So combustion is going to involve organic molecules reacting with oxygen to produce carbon dioxide and water. Combustion reactions are going to tend to be very highly exothermic. They're going to tend to be considered irreversible. And in general, they are definitely going to be irreversible because you're going to lose the gases involved in it. Combustion reactions are going to be types of decomposition reactions. Typically, these are referred to as oxidation reduction reactions. You're going to see oxidation reduction most normally as redox. Okay? REDOX, which is the abbreviation, and chemists are lazy, so. Yeah. Redox. Combustion reactions are going to use oxygen, and they're going to produce energy. This is why, for example, they're the most common production of energy on the planet by a long shot. Okay? There's very few production of energy on this planet that is not a combustion reaction. Okay? And overall, almost all reactions that produce energy are redox reactions, in fact. That is a very, very common method to produce energy. These reactions are very important in understanding any type of fuel, whether that's the fuel in your car, but it also could be the fuel in you. Okay? Because redox reactions are what you use to power your cells. Okay? And the reactions inside your body are actually very similar to a combustion reaction, just not an actual combustion reaction because it's not highly exothermic. All right, so again, we have the products. These are always going to be carbon dioxide and water in combustion reactions. They're going to be a useful place to start for when we explore our organic chemical reactions because they're the ones you probably understand the best you've probably seen the most and you're the most familiar with. Okay. So alkanes, remember our alkanes? Those straight chain carbon chains? Okay. Alkanes are generally going to be considered on-reactive. When you're just sending them around, gasoline's not usually considered super reactive, right? It's not like you touch gasoline and boom. All right, so they do, however, undergo combustion. And they do that spontaneously and very energetically, right? Alkanes are excellent fuel sources because they give off a lot of energy when they're burned. They're very, very energy dense. Okay? And that's why they have won the crown and still are winning the crown for fuel for transportation, right? And sadly, they're still winning the crown in almost every other energy production as well. It is. Yeah. Yeah. So internal combustion engines emit partially reacted hydrocarbons in their exhaust. This is actually one of the big problems when you're talking about exhaust with internal combustion engine is that soot. You ever seen the black stuff that builds up around the tailpipe? It's called soot. If you hold something against that, it build up against that, right? That is actually on-burn, on-combusted alkanes. Okay? So you get little partially combusted alkanes coming out. And they stick to stuff and cause a variety of health and environmental damage issues. So other hydrocarbons are not completely oxidized, and carbon soot occurs, of course. The term clean burning actually refers to the efficiency of the combustion. The cleaner a fuel burns, the more complete the combustion is, and the more closely you get it to carbon dioxide and water. Okay? I know that very famously in the media and very famously in politics, people have considered CO2 as to be this huge pollutant. Of the pollutants, CO2 would be one of the most benign. Okay? And in fact, do you guys know what 2/3 of global warming is? Okay, CO2 accounts for less than 1/3 of global warming. Okay? Does anybody know what 2/3 of it is? Huh? It isn't, but that was a good guess because methane is 30 times more effective than CO2 at global warming. So it's water. Water is actually the more dangerous pollutant in terms of global warming of those two. But what can we do to reduce water? Absolutely nothing, right? That just goes in the atmosphere depending on temperature. So, can't do anything. And so we completely ignore it, even though it is the more dangerous of those two in terms of pollutants. Okay? In terms of danger of pollutants, you can't get much more benign than water, CO2, and then the safest pollutant is nitrogen. Makes up 70% of the atmosphere anyways. Okay? Unfortunately, we can, no matter what it is, even if it was nitrogen, we could actually put out enough nitrogen to mess up the planet. It would be possible. It would be really, really tough to do, though. Okay? Okay. So don't take it as I'm going to put out like a trillion tons of nitrogen every year. Prove Dr. Clausen wrong, okay? You can prove me wrong. Nitrogen could damage the atmosphere if you put enough of it. Okay. So, distinguishing chemical reactions. How do we tell one from the other? For many organic reactions, the interesting part is how the functional groups change as your reactants form products. And that's why we focus so much on the functional groups, and they were very important in the naming of them. Okay? Because they're going to greatly determine what sort of reactions you can do, what you can do with the molecule, what it does in your bodies. Okay? For example, what happens when you drink alcohol? Nobody? Oh, I know you guys know something about alcohol. We're in Tennessee here. It's not possible you not at least know of it. All right, so you drink alcohol, and is it a poison? Yes. Yes, alcohol is a poison. Everything is toxic in the correct dose. Okay? Everything is a medicine in the correct dose. Right? That's the toxicologist motto. So, dose is everything, including water, right? If you get enough water, you drown, don't you? Okay. So, if we have alcohol, what's the primary symptoms of alcohol? Nobody?
Dehydration.
Yeah, dehydration, major symptom of alcohol. Why people drink a lot of water afterwards. Helps you out. One of the major symptoms of alcohol is suppression of your inhibitions. You can actually start having hallucinations in large enough doses. Interestingly enough, if you have long-chain alcohols or things that are more organic, larger chained, larger rings, that sort of thing, those alcohols become much more toxic, but they also have their hallucinatory properties increase tremendously. And so you start experiencing more hallucination properties. Yeah. And they become much more effective at getting people drunk. Of course, they're more toxic as well. Okay? Does anybody use the dang, you know the new dishwashers? They all have that rinse aid. Anybody use that junk? That stuff just makes me go, why would you put that in with what you're going to use food on? It's long chain alcohols that they use for that, and they're actually quite toxic. Yeah. I have no idea why you would put that on things you eat from. It really, really makes me question what the hell's going on. Anyways. Now, this right here is organic chemical equations. We have the structures here of organic molecules. We show the connectivity of these and their functional groups. You'll see here we actually have a double bond, don't we? Everybody see that double bond okay? Okay, so the small molecules can participate in the reaction are shown with the reaction arrow, and reaction conditions are going to be shown above and below the reaction arrow. The stuff above the reaction arrow, those are things that you're going to use in the reaction. They're reactants. Typically, they're very small molecules that are not quite as important for their structure. Okay? So you don't care what their structure and connectivity are like. Okay, so that's above the arrow right here, right? Below the arrow is the conditions you're doing it under. It's things that are not going to react in the reaction, or they're going to be catalysts. So right here we have a platinum catalyst. Okay, that speeds up this reaction tremendously. It could be something like a solvent. If we were doing this reaction in alcohol, you'd see alcohol down here, usually as ETOH, which is ethanol. Okay? And so you could put things like a solvent, you could heat it, you could expose it to high frequency light, you could put whatever reaction conditions you need. Okay? Okay. And so this right here is what's called hydrogenation. Anybody ever heard of hydrogenated oils? Or peanut butter? Okay. Okay, this is what you do to peanut butter actually. Okay? This would be like peanut oil, has a double bond in it. You do hydrogenation by adding H2, two hydrogens across it, break the double bond. That gives you something that melts at a slightly higher temperature. Okay? And that slightly higher temperature happens to correspond to about the temperature of baked bread. Okay? Heated bread. Which makes the peanut butter nice and soft and gooey, right? And so, yay, peanut butter on toast. Okay, so we distinguishing, again, chemical reactions. Biochemical reactions are going to be written just like organic reactions. The reactant and product and the reaction conditions will be shown. However, biochemical reactions are oftentimes coupled. So you actually have multiple reactions, usually two reactions, that are happening simultaneously. One provides the energy, the other gives you what you actually want as the product. Okay? And that's what we're seeing here. We're actually seeing ATP being used to set up glucose so you can break it down and get more energy from it. Okay? And so you'll notice that the two arrows in the reaction are actually two reactions going on. So what we have here is we have glucose reacting with ATP. ATP goes to ADP. glucose goes to glucose 6-phosphate. This happens in the presence of a catalyst here, which is an enzyme, which is this hexokinase. By the way, the enzymes have a very specific naming. Hexo meaning 6. Let's see the 6 carbons. Kinase specifically refers to using ATP here. ACE means enzyme, in case you're wondering. Okay. Okay, does anybody have any issues reading this reaction here? See how we're just building up the language? Building up the ability to read these things, right? Okay. And now you can actually follow along chemical reactions in a biological system. So again, this is an overview of these chemical reactions. We have the general reaction, organic reaction, and biochemical reaction, and then a breakdown of the various different points. So let's talk about oxidation and reduction. So we have redox reactions, oxidation reduction reactions. So there's a few different ways that we can go ahead and follow a redox reaction. In every redox reaction, it's always going to be a duality, okay? And that is that you have an oxidation that's going to happen, and you have a reduction that's going to happen, right? And so what an oxidation reduction is oxidation is going to be where you lose an electron. So right here, we actually have this item here, this atom, being oxidized to this, okay? And so we have lost an electron, and we have oxidized it. This right here is going to be an atom or molecule that is being reduced. So reduction is occurring to this, and it is gaining electron. So remember, electrons are negative. So if you gain an electron, you are reduced, aren't you? Okay, you gained a negative. You gain negatives, you're reduced. Okay. Oxidation, on the other hand, is where your oxidation number goes up. Okay, the most common oxidizing agent, the thing that oxidizes stuff, is oxygen. That's why it's called oxidation. Okay, so oxygen always oxidizes things. That's sort of one of the easy ways to remember these. Okay, so if you lose an electron, you are what? Oxidized. Everybody with me? Lose an electron, you are oxidized. Gain an electron, you are reduced. Okay. Okay, so a reducing agent is going to reduce something else, right? Does an assassin kill themselves? Life would be better if they did, but they don't. So, if you're a killer, you kill someone else, right? Okay. So this is a reducing agent. It's going to reduce something else, right? An oxidizing agent is going to oxidize something else, okay? So oxidizing agents are themselves always reduced. Reducing agents are themselves always oxidized. If you have an oxidation, can you ever have an oxidation without a reduction? No, you have to have one of, if you have the other, right? If you have a loan, you have to have a lender, don't you? Okay? If you have a thief, you have to have somebody that got stole from, right? You always have to have both. Okay? All right, so anybody have any questions about these terminologies so far? Discussing redox reactions without these is going to be totally impossible. Okay? So it's very important you have some idea of this terminology. So when we're looking at these, this oxidation reduction terminology I just gave you is always true, okay? If you're oxidized, you always lose an electron. If you're reduced, you always gain an electron. That's always true, okay? This is considered in your book, and by most, by your book really, as the inorganic way of looking at this, okay? And so this is the chemist's way of looking at this usually. Biologists oftentimes use another way of looking at this, which is mostly true, but not always. Okay? Again, this is always true. This is true for what I'm going to say next as well. Okay? It's always true. All right. So another way to look at this that makes this faster to deal with is that if you gain an oxygen, you've been oxidized. So if you have something that gained an oxygen, it got oxidized. Okay? If you have something that lost an oxygen, it got reduced, didn't it? Okay? If you have something that gained a hydrogen, that thing's been reduced. If you have something that's lost a hydrogen, it's been oxidized. Okay? And so it's a real easy way to look at these. You can very quickly tell in 90% or 99%, something like that, of all biological reactions, which has been oxidized and which has been reduced. It's almost always true because all biological reactions happen in water. And so there's oxygen and hydrogen in everything. Okay? There are exceptions. There actually very much are exceptions. Okay? But those exceptions are incredibly rare. And it's unlikely any of you will actually see these reactions. Okay? They happen in the human body, they do, but it would be interesting if you actually saw them. That'd be pretty cool. If you ever do, let me know. All right, so again, this is an inorganic oxidation reduction. So rusting is a great example of a redox reaction. We have the iron metal here, which is in steel and iron and all those different metals that you're thinking of. Okay? And then oxygen is actually going to react with that iron. That's going to form iron oxide, which is this right here, which we typically colloquially refer to as rust. Okay? All right, so the atoms that lose electrons during the chemical reaction, these are going to be said to go oxidized, and you can see that the iron is what gets oxidized. Okay? The atoms that gain electrons, which is the oxygen, are said to be reduced. And so the reduction occurs to that. The oxidized species is always the reducing agent. So the iron here is the reducing agent. Metals in general tend to be reducing agents. The nonmetal here, which is the oxygen, is the oxidizing agent. Again, that's the one that got reduced. Okay. So the inorganic oxidation reductions, again, one of the ways you can remember this, if you can't remember it based off. Okay, so personally, I think you were reduced, you lost, you gained an electron. Electrons are negative is easier to remember. Okay, and I've had more luck with people remembering that, right? By a lot. These acronyms have actually been shown in every study ever done on them to not actually help, because the people remember the acronym, don't remember what the heck it translates to, and then congratulations, you have a useless acronym. Okay, but I'm going to give it to you because for some of you, in my experience, something like 20% of you, this is going to be the way to go. Okay, for the majority of you, you're going to be better off remembering reduction, reduced because of negative electron. Okay. Okay, so oil rig, which stands for oxidation, is loss. Reduction is gain. Right? So again, metal atoms tend to lose electrons. They tend to form cations. Remember, we always formed cations with the metals, right? The positively charged ones. And so those get oxidized. Their oxidation number goes up. They lost a negative, which is an electron, didn't they? Non-metals gain electrons. They're going to form the anions, the things with the negative charges. And so they are reduced. They become negative. And that's because they gained electrons. Oxidation reduction reactions are always going to be coupled. They always have to happen together. All right. So this right here is another example of a biological redox reaction. So in biological systems, metals are also oxidized and reduced. In fact, many of the pathways that would have a lot of oxidation reductions actually happen in biological systems where we have metals. They'll play a key role in that. Okay? So, for example, we have the protein called cytochrome C. It's actually going to play a very important role in ATP production. We actually see the same repeated pattern along the citric acid cycle / electron transport chain. Anybody heard of those two things before? Not yet? Okay, might be a little too early in some of your careers to have heard about those. If you end up taking the biology and the microbiology, you'll hear more of that stuff. Okay. Okay, so the protein contains Fe2 plus, undergoes the oxidation to Fe3 plus, followed back by the reduction to Fe2 plus. This iron ion right here is the one that gets oxidized and reduced repeatedly over and over. It's actually held in place by a molecule right here that's called a heme. This is a heme group. Anybody heard of hemoglobin? Okay, that's named after the 4 heme groups it has. Okay, so it also has a heme group like this. In that case, it's actually binding to oxygens to transport them. Okay, this is another use for that same sort of metal heme group again. Okay, there's also very analogous structures which have things like manganese, magnesium, copper, etc. Okay, and those also play roles in usually oxidation reductions. So let's talk a bit about the organic oxidation reductions. So an organic molecule is going to be oxidized if it gains an oxygen or loses hydrogen, reduced if it gains hydrogen or loses oxygen. So right here we actually have a carbonyl, and you can see here that we oxidize it and it goes to carboxylic acid. And that's because we've actually gained another oxygen. See that? We gained an oxygen on that structure, so it's been oxidized. Okay. Right here we had the aldehyde again, so we reduce it and it goes to the alcohol. Okay. Anybody know what happens when you've been out at night drinking? What your liver does? Okay. So you drank a bunch of alcohol, right? Specifically ethanol. Okay. What's going to happen is your body is actually going to oxidize it until it goes to CO2. Okay. And so the first things that does to it, it goes ahead and oxidizes it, and that's going to form something that's very analogous to formaldehyde. Okay? And so is that good for your liver? Sound like a great thing to have? No. No, it's actually quite damaging to the surrounding tissue. Okay? And so what's then going to happen is you're going to then, again, oxidize it again, and that's going to actually go to acetic acid, which is not as bad for your liver. Okay? And at that point, you can actually urinate that out if you're producing too much of it, but your body will actually attempt to go ahead and oxidize that again and go to CO2 eventually. Okay? Because it can use it for energy. Alcohol does get digested down to energy, in case you're wondering. Now, anybody know what happens if you get methanol? Anybody heard moonshine will make you go blind? Okay? And that's because you can produce wood alcohol. If you do a bad job purifying your alcohol, like you take the lead, do you guys know what the lead and tailings are? Okay, so when you purify alcohol, what you're doing is you're boiling it, you're cooling it down on the other side. Okay? And so if you take the stuff that comes off first, sometimes that's methanol, right? Really, it's usually not a huge issue for most moonshine distilleries. It was only really became bad back in the Prohibition era because the mob just started selling wood alcohol, methanol to people as actual alcohol. And so they just knowingly sold the poison to people and killed them. Yeah. But, yeah, it's dark. If you're ever looking at Prohibition, it's really nasty. Okay. So if you do the same thing with methanol here, okay, what you end up getting is, again, you get something pretty analogous to formaldehyde, and that's not great for you, okay? But that just causes a bit of liver damage. What ends up happening is you actually oxidize it even further. And anybody ever gotten bit, quote unquote bit, by an Asian beetle or ant? Okay, what they actually do is they spray you with something called formic acid. And formic acid is actually a very toxic to you. Okay? It actually tans your flesh, kills your cells. And so when you drink methanol, that's actually what you form, and that's highly soluble in your blood too. So it spreads out very quickly around your blood. Yeah. And so it causes a lot of damage in the area. It can cause a lot of damage to things that are very sensitive, for example, your eyesight. Okay. Formaldehyde, by the way, is actually a poison as well. That's actually why we use it in preserving corpses and stuff, because it's toxic to bacteria. Okay. Okay. Anybody have any questions? All right, we'll go ahead and start up here next time. You all have a wonderful day. I will see you all Thursday. And then I won't see you all for a week after that.